Well, I'm really excited to be here today because I get to share with you how we're changing the future of concrete with biochar. There's been a lot of talk about the importance of reducing greenhouse gas emissions. And a lot of industries have invested a lot of their resources in greener technologies to make this goal a reality. But unfortunately, global greenhouse gas emissions are still increasing. And did you know that 2/3 of that increase is attributed to the concrete industry? Most of this is from the cement production. In this process, we take limestone, or calcium carbonate, and we heat it up to get calcium oxide. And while this is an energy-intensive process, the bigger problem is that when we convert calcium carbonate to calcium oxide, we kick off CO2. That means unless we fundamentally change one of the main ingredients of concrete, that ordinary Portland cement, we're stuck with the CO2 emissions. And here's the main problem with that. No alternative ingredient can match ordinary Portland cement's combination of cost, quantity, and quality. I got involved in this line of work because I find concrete fascinating. And I'm willing to bet I'm the only person who has ever told you that. And I know it sounds a little weird, but hear me out on this. Here's this material that's been around for millennia, and we still don't really understand how it works. Don't get me wrong, we've made a lot of improvement in our understanding, and scientists are learning more every day, but a lot of it still remains a mystery after all this time. It's also a material that is abundant all throughout the globe. So that means that if we can make even the smallest improvement to the material, we can have enormous impact to the global economy and environment. For example, if we can reduce the carbon emissions associated with concrete by 48%, we can avoid pumping 1.3 gigatons of CO2 into the atmosphere every year. And that's exactly what our technology can do. We accomplish this by replacing part of the ordinary Portland cement with a material called biochar. So, what is biochar? Biochar is a carbon-rich material that is a byproduct from the biofuel industry. It's produced through the fast pyrolysis of wood or other biomass sources. And in other words, that means that we heat the biomasses up to high temperatures very quickly in a limited oxygen environment. And the end result is a highly stable carbon form. So instead of the biomass decomposing and releasing CO2 back into the atmosphere, the carbon is sequestered, bound up into the structure of the biochar. So the CO2 that was absorbed during the plant's life cycle, that stays trapped. I was first introduced to the concept of using biochar as a concrete additive through a colleague at NREL, which is the National Renewable Energy Laboratory, for those of you who don't know. He had found a few papers trying it without much success, and he thought, you know, I bet I could do better with the high-quality biochar produced by NREL. And so he tried and made some spectacularly bad samples and realized, oh, maybe I should consult with someone who actually knows something about concrete. So he reached out to me, and our partnership was born. He provided the expertise on biochar, I provided the expertise on concrete, and we worked together to produce something truly transformational. The innovation is actually quite simple. And in an industry where new is usually considered a risk not worth taking, simple is actually a really good thing. We basically developed a new recipe for the concrete, replacing some of the ordinary Portland cement with biochar. And in testing our design, we realized there were 4 key things that we had to control. 1, we have to mill the biochar. Since the biochar is produced from wood, it retains some large pores. So if we introduce it into the concrete without first milling it, we add unnecessary porosity to the concrete, which ultimately decreases the strength since air doesn't contribute anything to strength. Second, we realized that even though the biochar does absorb some of the mixed water, We don't have to add any additional water. The biochar will release the water over time, curing and hardening the cement into a stronger and denser mix. In contrast, if we add more water, we decrease the concrete strength and actually its durability. Third, to get similar flow properties to a conventional concrete, we realize that we have to increase how much superplasticizer we use. This is a chemical admixture that is regularly used in the concrete industry to adjust the flow of the concrete without adding additional water. It's already commonly used, we just require a bit more. Since the biochar absorbs some of the mixed water, if we don't compensate for this with additional superplasticizer, the mix won't flow quite as well as a conventional concrete. And this is important because if the concrete doesn't flow well, it can leave behind trapped air that stick around as voids when the concrete hardens. And again, this will decrease the strength of the mix. Finally, the properties of the biochar itself should be controlled to maximize its beneficial use in concrete. Most of our work has focused on that fast pyrolysis biochar produced by NREL. This is a biochar that's made primarily from softwoods. But depending on the feedstock source that you use or the processing parameters, the biochar properties can vary pretty significantly. We're currently trying to understand how much variation we can tolerate in the biochar properties for the biochar to still be useful in concrete. But we do know that the properties of that NREL biochar are optimally suited for strength gains in the concrete. And this is something we can predictably control. So clearly, we've solved concrete's emissions problem, right? Well, it's not quite that simple. Although we are significantly reducing the carbon footprint of the concrete, and we do improve its strength at the same time, at these higher biochar loadings, the flow of these mixes isn't quite what a conventional concrete is. And this is an area where contractors can get pretty finicky. If it doesn't flow exactly like the concrete they're used to, there's going to be some concern. So we still need to address the flow at these higher biochar loadings. Otherwise, we're limited to mixes with about 5% biochar. These behave almost identically to conventional mixes, but they only offset the CO2 emissions associated with concrete by about 16%. And while this still is very helpful, we have our sights set on something bigger. We have our sights set on a carbon-neutral concrete that's actually stronger and more durable than traditional concrete. Thank you.